So Math 102, Notes 9, page 1. I might get into a little bit of 2 possibly if the video doesn't get too long. We're going to simplify. Assume all variables are positive, so we're not going to need to worry about absolute values. Notice the first question I ask myself. This is what I do. How many terms? That's critical. We're still asking that question. There's 2 separate terms. Well, when there are 2 terms, are they like? Well, it doesn't look like they're like terms. That's a root 8, that's a root 32. Those are different values. So we can't put them into one pile just as yet. But in the past, we've seen that, you know what? If we simplify within each term, then I just might find out that I have like terms. So can I simplify within each term? And the answer is yes. Because I look at the square root of 8 and I say, you know what? 8's not a perfect square itself, but it does have a perfect square that divides into it, 4. That means I can simplify square root of 8. So this is going to be 3 square root of 4 times 2. The square root of 4 is 2, so I'm going to take the square root of 4. That comes out of the radical as 2. It gets multiplied by the coefficient that was already there. This term is a 6 root 2. I have 6 root 2 coins. All right, well, it still doesn't look like the square root of 32, but can I simplify the square root of 32? Gotta watch out. 32 is one of those numbers that has 2 square roots that divide into it. You want the biggest. So the biggest square root that divides into 32 is 16. So, yep, I can simplify this. Square root of 32 is the same as the square root of 6 times 2. I'm going to take the square root of 16 separately. That comes out as 4. And the square root of 2 stays under the radical. So I simplified within each term. Lo and behold, those are both radical 2 terms. I have 6 of them here, 4 of them there. I have 10 of these radical 2 coins, and that is simplified. So now, normally if I was doing this in class, this is so typical, I do this fairly easy one and I say, all right, you try this one, and it looks harder, but it isn't. It really isn't. So give it a shot. Turn off the video. Try it. I'm going to go ahead and start it. How many terms? That's my first question. It's 2. And are they like? Well, they don't look like they're like terms. But can I simplify? I think so. I'm looking at those radicals. I think so. So let me focus on this first term. Well, 3 is not a perfect square, and no perfect square divides into it, so I can't touch the 3. But x cubed, now that's not a perfect square. But remember, the index is 2, so if the exponent's bigger than the index, I can pull something out. I need an even number for my exponent for this to be a perfect square. Well, the even number smaller than 3 is 2. So I would write this as the square root of 3x times x squared. Notice I am using my exponential rules here, because when you multiply the same base, you add the exponents, so this is still the same as x to the 3rd. I am not changing the expression, I'm just changing its form. Looks like an exclamation point, doesn't it? The square root of x squared is just going to be x, because we're going to assume x is positive, so we don't have to say absolute value of x. So it's 5x. Take the square root of x squared, that comes out as x. Leave the root 3x under there. So this term winds up being 5x squared root 3x. Okay, that's as simple as I can write that one. Now let me look at the other term. All right, the 12, that's not a perfect square, but a perfect square does divide into it, so I can definitely work with that 12. I can write it as 4 times 3. And then the x to the 1st, I can't do anything with it. The exponent's smaller than the index. So that x is staying there. I can take the square root of 4. That's going to come out as 2 because the square root of 4 is 2. And the root 3x stays under there. And then 6 times 2 is 12 minus 12x squared root 3x. Now I look at my two terms. And for practical purposes, it's best to see x squared root 3x as the type of animal. And they are the same animal. So I have 5 of them here. I lost 12 of them there. That's minus 7x squared root 3x. Now, when you do your homework, you're not always going to wind up with like terms. So just know that. For instance, this one here. Now, it's already filled in. I'll just go over it briefly. You know, when I did these notes in class, I was running out of time, so I had to skip this one. So again, it's the same idea. It's 2 terms. Simplify within each term. Here, a radical divided by a radical, you can make one big happy radical and reduce inside. The x to the negative seconds, they cancel. 12 over 2 is 6. The y's cancel, that's just root 6. Here, when you're multiplying 2 radicals, you can make one big happy radical. Combine the product under the radical. Notice you have opposite exponents here. You add the exponents when you're multiplying the same base. You get m to the 0. Remember, m to the 0 is 1, as long as m is not 0. So these essentially cancel out. You get root 5. Those are unlike terms. Root 6 minus root 5, can't simplify. You're done. Okay, so that's basically the type of problems you'll be dealing with when you're adding or subtracting 2 different terms with radicals. The other thing we can do is use the distributive property with radicals. So let's look at this expression. Notice it's really all one term, because I'm going to think of it as root 3 times this mess in the parentheses. That's multiplication. That's all one term. But it's multiplication to several terms inside the parentheses. So this whole idea of terms does get complicated. Big picture, it's all one term. But if you look inside this factor, there are 2 terms. So if you're going to multiply to several terms, you use the distributive property. Now I'm going to take every step and hope that you can condense this a little bit. Root 3 times root 6, I'm just going to write it that way. If you can say, oh, that's root 18, great. Minus root 3 times that term. Okay, the 5 stays outside the radical, then it's root 3 times root 3. Oops. And now let's simplify each term. Multiplying radicals, you can make one big happy radical, so that's the square root of 18 minus, now there's 2 ways to think about this. The fastest way, by definition, the square root of 3 times itself is that number that gives you 3. So root 3 times itself will be 3. If you're like, oh, I don't really believe that, multiplying under the radical, that gives you the square root of 9. And what's the square root of 9? 3. So if you can go straight to the 3 there, that's great. We do have to simplify this root 18. 18 is not a perfect square, but a perfect square does divide into it, 9. So I'm going to write this as 9 times 2. And this is going to be minus 5 times 3. So one last step. Square root of 9 comes out as 3. So this is 3 root 2. And 5 times 3 is 15. So this is 3 root 2 minus 15. Okay, so try this one. So again, see, I do the easy looking one and I give you the hard one, but it's really not any different. So turn the video off for a minute or so. Try it. Turn it back on when you think you have the answer. So I'm going to go ahead and do it. look at the big picture first. It's all one term. You have multiplication to this factor with several terms. That's the distributive property. Now there's a lot going on here, so you might want to just write more down. So this is the cube root of 3x times the cube root of 9x to the 5th, so distributing there, minus the cube root of 3x times the cube root of x squared. Our handy dandy radical rule says, hey, if you're multiplying radicals together and as long as their cube roots, square roots the same, you can combine it into one big happy radical. So this is the cube root of 27x to the 6th, okay? All right, minus the cube root of 3x cubed. And then see if you can simplify each radical. Don't forget the step of checking for perfect cubes. Oh, is 27 a perfect cube? Yeah, it is. That's just 3. Is x to the 6th a perfect cube? Well, yes, it is, because 6 is a multiple of 3, or 6 is evenly divisible by 3. So cube root of 27 is 3. The cube root of x is 6. You actually divide the index into the exponent. That's just 3x squared. And then here, again, we do have a perfect cube. Cube root of x cubed is just x. And then you can't do anything with the cube root of 3. 3 is not a perfect cube. There are no perfect cube factors in there. That's it. You're done. So I think we'll go ahead and just keep this video at page 1, and next video will be page 2.